Yeah, good morning to all of you. In this lecture, I will discuss about the classical mechanics for any competitive examinations like NET, GATE, TIFR, and uh, any Central University PhD entrance test. So the classical mechanics is basically a scalar mechanics or analytical mechanics. Classical mechanics is scalar mechanics, or this is simply known as analytical mechanics or scalar mechanics. The basic physical quantity in this mechanics is energy instead of force, velocity, and momentum. The basic physical quantity is energy, which is a scalar quantity. So we will discuss about each and everything in scalar mechanics, because scalar, it is very difficult to take care of vector quantities, because in some situation we need to take care of its magnitude and direction. But in scalar mechanics we have we can simply add or multiply or subtract any physical quantity. That is the advantage of scalar mechanics over the vector mechanics. So, and who developed this classical mechanics? The major contribution is D'Alembert, Lagrange, and Hamilton. So they developed a mathematical tool in order to analyze the mechanical property of a particle or system of particle or any system. So D'Alembert, Lagrange, and Hamilton. So in vector mechanics we have very good tool to analyze the trajectory of particle, that is Newton's law. But in this case we have Lagrange equation of motion and Hamilton equation of motion. So using this equation of motion we can simply are solving this is basically a differential equation. The solution of the differential equation will give us the trajectory of particle. So in classical mechanics we will focus only on these particular keywords, which is Lagrange, Hamilton, D'Alembert principles. So Lagrange, we have a Lagrangian equation of motions, and Hamilton's equation of motion, which is simply a partial first order. Hamilton's equation is first order differential equation and Lagrangian is second order partial differential equations. So by solving the partial differential equation we will get the solution in terms of that solution will give us the trajectory of particles. So this is, and before starting the details of classical mechanics we should know the few fundamental keywords. That is, what is that fundamental keyword? That is, what is constant, what is generalized coordinate. So in classical mechanics we have very important keyword, that is, what is that keyword? Generalized coordinate. And next, equation of constraint and degree of freedom. Generalized coordinate, constraint, and degree of freedom. So these are three very important keywords in classical mechanics. So we will discuss it one by one. So the first one is constraint. Constraints. So what is constraints? Constraints is simply restriction or limit to the motion. Constraints are simply restriction or limit to the motion. Constraints are simply a restriction to the motion. So depending upon their property, we have two different types of constraints. So types of constraints. Or we can write it as, this is types of constraints. First is holonomic and non-holonomic. So what is constraint? Which is restriction to the motion or limit to the motion. It is two types. First is holonomic and another is non-holonomic. Holonomic constraints means which can be expressed in terms of equation, which expressed or which has following form, which follow the following expression. The expression or which can be expressed in the form of equation, which can be expressed in the form of equation, means f r1 r2 dot equal to 0. So which can be expressed or which can be expressed in the form of this equation. And non-holonomic which can be expressed in the form of inequality, which has following form. In another word, we can write it as which has following form, which is f r1 r2 r3 dot t greater or equal to 0. So this is the simple mathematical definition of constraints and their classifications, holonomic constraints and non-holonomic. Okay. Now let us analyze this mathematical definition in terms of example. So what is the example of holonomic constraints? For example, if we have a simple pendulum, which is very important system in physics. So simple pendulum is very important physical system. So example 1, simple pendulum. This is the schematics. What is simple pendulum? Simple pendulum is simply a system in which a bob of mass m attached to a massless string of length L. So this is known as simple pendulum. This is the schematic and this is the definition. If someone asks what is simple pendulum, means a simple pendulum is a system. In another word, we can say that simple pendulum is a system which execute a simple harmonic motion. So another question, what is simple harmonic motion? I just leave it to you. So simple pendulum is a system in which a bob of mass m attached to a massless string of length L. This is suspension point. So what is it? So this is holonomic constraints, which means what is L equal to constant. Means we can express our expression is directly equal to L is equal to C. So a holonomic constraints are the constraints which can be expressed in the form of equation. So this is the example. Simple pendulum means length of this string is constant. So we can write L equal to C, means in which a equation of constraints expressed in this form, L equal to this is FRT, which is equal to 0. In this case, this is L equal to C. Or in another word, we can write it as also R L minus C equal to 0. So this is the way to express the holonomic constraint and non-holonomic constraints. Now etude machine, another physical system, etude machine, or we can say that particles are constrained to move on the circumference of circle, whether this is holonomic or non-holonomic. If a particle which are constrained to move on the circumference of circle. So we have, I don't know, this is not visible. So this is one example. We have another example of this holonomic constraints. Example 2, particles are constrained to move on the circumference of circle whose radius is a. So particles are constrained to move on the circumference of circle whose radius is a. So this is r equal to a. We can write r equal to a, or r minus a equal to 0, or r minus a equal to 0. It means it can be expressed in this form. So any physical system which can be expressed in this form, we can say that is come into the category of holonomic constants. So similarly, we have a non-holonomic constants. We have non-holonomic which can be expressed in the form of inequality. Suppose particle in a box, we are inside the room, so we can roam throughout the room. So there is a equality, there is a, that is why there is a inequality sign if we have a gas molecule inside the container. Example, inside container. So this is gas molecule which is inside the container. We have no idea whether this molecule is, if the container whose side is L, whether it is at this position, at the end position, or in between, or somewhere at the center, or somewhere else. That is why there is a inequality sign. Particle in a box, we are inside the room, so that is inequality. So gas molecule inside the container is the example of non-holonomic constants. Particle in a box, this is one. Particle in a box whose size is 0 to a. So particle in a box is another example of non-holonomic constants. Motion of particle on the surface of a sphere, that is also non-holonomic constants. So this is the way to define the constants, which is, so we have constants is the restriction to the motion or limit to the motion. It is two types, holonomic constants and non-holonomic constants. Holonomic means which can be expressed in the forms of equation, means FRT equal to 0, exact equal to 0. And non-holonomic means which can be expressed in the form of inequality. For example, gas molecule inside the container, particle in a box, we are inside the room. So there is a inequality, whether we are at the boundary or in between or somewhere else. So, and holonomic means particle constrained to move on the circumference of circle. It means particle restricted to move on the only on the circumference of the circle, which means particle only move at r equal to a. So r minus a is exact equal to 0. So that is, this is holonomic constants. So I think it's all about the concept of constants. Next we have a generalized coordinate. Generalized coordinates. So generalized coordinates are the minimum number of independent coordinates required to specify the motion. So minimum number of independent coordinate require or needed to specify the motion of our physical system. So generalized coordinate, this is very important keyword in classical mechanics. So minimum number of independent coordinate required to specify the motion of our physical system. It is represented by letter Qy or Qj. This is generalized, symbol of generalized coordinate. This is simply symbol of generalized coordinates. See, once you fix the generalized coordinate, corresponding velocity is automatically fixed, and it is not necessary that this generalized coordinate is only a dimension of length. It could have any dimension. If it's up to us. If our generalized coordinate is position, then what is? So I will just give you the tables which tells us the information about the generalized coordinate and corresponding generalized velocity. So generalized coordinate is simply, this is the tables. Of generalized coordinate and corresponding velocity. So if our coordinates, so this is generalized coordinate, so first is if we have a length, our generalized coordinate is length or position, which is Qj. So this is generalized coordinate and this is generalized velocity. So what is corresponding velocity? This is Qj dot. Dot means dq by dt. Qj dot means dq by dt. So generalized coordinate is minimum number of independent coordinate required to specify the motion of our physical system. This is, if you fix the generalized coordinate, it has any dimension. We can, in another word, we can say that our generalized coordinate has any dimension. It depends upon us. If our generalized coordinate is length or position, then it has dimension of L. If our generalized coordinate is velocity, it has different dimension. And once we fix the generalized coordinate, corresponding velocity automatically fixed. In this case, if our generalized coordinate is length or position, so generalized velocity is Qj dot, which is dq by dt, What is, if our generalized coordinate is linear momentum? In linear momentum. Second, if our generalized coordinate is linear momentum, let's say our Qj is P simply. So what is our generalized velocity? Our generalized velocity is Qj dot, which is P dot, which is dp by dt. So rate of change of momentum, which is force. So in any competitive exam, someone asks that if you have a profile, if your generalized coordinate is basically linear momentum, so what is the corresponding generalized velocity? If your generalized coordinate is simple position, so what is corresponding generalized velocity? If your generalized coordinate is angular momentum, if your generalized coordinate is angular momentum, it means our Qj is J. If this J is angular momentum, so what is our Qj dot? Generalized velocity is again J dot, which is dj by dt, rate of change of, what is this? This is rate of change of angular momentum, which gives us torque. Means we are talking about rotational motion, tau or torque. So it's up to us. See, once we fix the generalized coordinate, this is generalized coordinate, the corresponding generalized velocity automatically fixed. So in this case, length is generalized coordinate, so our velocity is generalized velocity. In this case, our generalized coordinate is linear momentum, so corresponding generalized velocity is p dot, which means rate of change of momentum, which is force. In this case, our generalized coordinate is angular momentum, so corresponding generalized velocity is torque. So this is just a table. If our generalized coordinate is energy, and our generalized coordinate is energy, it means our qj is E. So what is our qj dot? Qj dot is E dot, which is rate of change of energy is power. Dimensionally this is power. So that is generalized coordinate has any quantity. So we can express generalized coordinate, number of independent coordinate required to specify the motion of our dynamical system. So once we fix the generalized coordinate, corresponding generalized velocity automatically fixed. And we have another information that generalized coordinate is number of generalized coordinate is equal to number of degree of freedom. This is another information, very important information, which help you in any competitive examination to tick out the objective questions, that our generalized number of generalized coordinate is equal to number of degree of freedom. So it's all about the constants and generalized coordinates. In next lecture I will discuss about the concept of degree of freedom. It's all about. Thank you.